Okay, we're told that the solubility of silver phosphated water is 4.3 times 10 to the minus 5. What is the Ksp for silver phosphate? All right, well, let's start this solution with the reaction that occurs when silver phosphate, the insoluble solid, decides it wants to dissolve in water. So it's going to form 3 silver ions, aqueous, and a phosphate, 3- ion, aqueous. Okay, because there's a subscript 3 here, that means when this breaks apart into component ions, there's going to be 3 independent silver ions in solution. Well, this is an equilibrium process, so why don't we set up our Rice table to answer the question. So we'll make our columns and our rows for our table. Every compound gets a column. And just like we did with water when we deal with Rice tables for acids and bases, because it was a pure liquid, we just X'd it out. Well, we're going to do the same thing with the silver phosphate because it's solid and it's not included in the expression for the equilibrium constant. And the Ksp is the equilibrium constant for these solubility problems. And so initially, we're going to say at the moment before any of this starts to dissolve, we initially have 0 amount of that and 0 amount of that. Well, we know that some of it will dissolve. Okay, it's going to shift to the right, and so we're going to lose, let's say, X amount of the silver phosphate, so minus X there. And then, if you don't mind, I'm going to skip over here to the phosphate, because for every one of these that dissolves, I gain 1 of the phosphate, so I'll put a plus X there. But for every one of these that dissolves, I get 3 silver ions, so I'm going to put plus 3X there. Okay, so then with just like every other Rice table problem, I'm going to bring my columns down, so 3X there and X there, right? Now, one important thing to note is that X is meaningful. That X is the amount of silver phosphate that dissolves. That's one way to think about it. Okay? So that X is like the amount of this that we lose, the amount of this that actually goes into solution. Well, we're told what that is. We know that that is equal to 4.3 times 10 to the minus 5. Okay? So we know the value for X. Now that's going to be useful here in just a second, because we're asked to find the Ksp. Well, let's write an expression for Ksp first. Just like every other equilibrium constant expression that we've written, it's just the concentration of each product, where we raise it to the power of its balancing coefficient, and then we leave out solids and pure liquids. So it's going to be the concentration of the silver ion raised to the power of 3 times the concentration of the phosphate ion. And we leave out the reactant side because it is a solid. Okay, so now we can just substitute in these terms from our table into this equation. And so the Ksp is equal to 3x cubed times x. Okay? Well, the nice thing is I know the value of x. It's 4.3 times 10 to the minus 5. So I can do a substitution and say, okay, well, that's going to be 3 times 4.3 times 10 to the minus 5. All that cubed times 4.3 times 10 to the minus 5. Okay, and if you do that math, you get 9.23 times 10 to the minus 17. That is the Ksp for silver phosphate.